Okay, welcome everyone. I'm just making a video to finish off this unit on measurement, and we're looking at mass and temperature. What I'm trying to do now is, in this introduction, talk a little bit about mass, and I think most of our world we're buying things in either grams or kilograms, depending on what we're purchasing when we're out shopping for groceries, for example. We may see milligrams, that's 1/1000th of a gram, on the side of some of the medicines that we use. The active ingredient that we're using in those medicines may be just a tiny amount, and so there's an example of where you might see milligrams. And the other thing, if we're buying things in bulk, we weigh those in metric tons, and often you drive the truck across the weighbridge, and there's a couple of questions there that work where you need to understand that an empty truck has a certain mass, and then you load it up with grain or potatoes or whatever you loaded the truck up with, and then you put that on the weighbridge and you weigh it, and that the difference between the tare amount, which is just an empty truck, and its gross amount is the load on the truck. So there's those sort of questions, and there's when we're dealing with temperature, we're working in 3 different scales. We've got degrees Celsius, degrees Fahrenheit, and scientists use degrees Kelvin. So we'll focus in on converting between those 3 scales, because I don't think that's difficult, and there's a couple of good questions here where we can work on those things. But I think it's handy to understand and navigate our way around our world by understanding what temperature water freezes at, and that's at 0 degrees. Okay, and water boils at 100 degrees. I couldn't hold this cup if this was boiling water here, but they're common, I guess, landmarks in our scale of degrees Celsius, and that's where this scale is come from. So we have to set 0 at some point, and we've just chosen to set it at the point where water freezes. Okay, so what this end of this chapter doesn't do is give you a really good way to tie all this understanding between measurement, liquids, mass, and temperature. It doesn't tie them all together. And the way I've thought about it is, and what I've set up here for you, I might raise this glass again to the camera, and you can see, even with water, depending on the temperature that it's at, we've got ice floating here in the water, and if we get a real scientific understanding of what's going on here, we know that water expands when it freezes, so it becomes less dense. Alright? And there's other things that we need to keep in mind too when we're doing this work, and I'll explain a bit more to you in the class, but it's handy to show you these things. Here's some water with olive oil floating on the top. So if this is fresh water, I think water is most dense at something like 4 degrees, and I use a conversion of 1 cubic meter of water is equal to 1,000 kilograms. So this olive oil here is less dense than water because it's floating on the water, and I think its density is something like, don't quote me, but I think it's something like 920 kilograms per cubic meter or something. So what I want to show you now, just quickly, and I think it's a perfect way to tie all this stuff up, because you might be thinking, oh well, what does that matter? What does that matter? And here's the olive oil as a classic example where just imagine if you had a cubic meter of water that weighed 1,000 kilograms and a cubic meter of olive oil that only weighed 920 grams or something, maybe even less. If you had to lift those up with a forklift or a crane, well, those measurements are important because there's a difference in the mass. And where that really comes into play is I've got my little origami boat here, and it's floating on the water perhaps. And the way we think about it is this. You've got the weight of the ship and you've got the weight of the cargo in the ship. That's making the boat sink down into the water. But to counteract that, you've got a buoyancy force pushing up against the bottom of the boat. And that is allowing this boat to float. Okay? And we're talking on a large scale here, hundreds of thousands of kilograms of mass here. So, and you've got the water pushing up against it in the port. Now, if that boat was being loaded in a freshwater river or something, it would sit lower in the water compared to seawater where it would rise up. So, people have thought about this kind of stuff, and we've got things called, here's another one of my boats here. We've got a couple of things that you'll see in the middle of boats when you're down at the wharf on the big cargo ships and you have a look at these sort of things. Maybe the camera picks this up, I'm not sure, let's try. We've got a couple of marks in the middle of the ship that tell us certain things. So I'm going to swap that out for this card here. Now, there's often a circle and there's often letters, and those letters don't mean much really. But what this circle and the line's doing is telling us whether the ship is loaded evenly across the length of the ship. So that has to be sitting level with the water, otherwise the ship isn't loaded correctly. So tying all this work together, we're thinking about a volume, and we're thinking about mass, and we're thinking about temperature of the water as well. And we're loading a ship, and we're hoping that this ship doesn't sink because the cargo in here is valuable. So these are the important marks here. We've got TF for tropical fresh water. So the water's warm and it's fresh. So when you load that boat will be sitting lower in the water. And then we've got a freshwater mark because we might be in a temperate region of the world, and the river or the lake might not, the temperature of the water might not be as high, so the water will be more dense. So the boat sits at a different level in the water, a bit higher. So then on this side over here, you've got saltwater marks here, and you've got a tropical mark, because even in salt water, just think about the Dead Sea. You can float really well in the Dead Sea because it's full of salt. Now, in the tropics, the water is less dense because it's warmer, and then you've got summer and winter marks that you have to be really careful how you load the ships, and they're international marks. And they're legal requirements for ships when they're loading, before they leave port. Someone's got to check these things and make sure the ships are good to go. So I really think that's an interesting way to wrap up all this knowledge. And hopefully you can see now that there's a lot of real life applications and links to the work that you're doing. So I'm just going to jump behind the light board and show you a few more tips and tricks to help you out and tie up this unit. Thank you. The other part of the work that we need to do is on temperature, and we've got the degrees Celsius here. Just remember to put a little circle, then a capital C next to your measurements here, because that's the unit that we're working in. And we've got, I've written down water, and H2O is a chemical symbol for water. And there's a couple of interesting reference points here. We're talking about when water freezes, and our degrees Celsius scale here is set up as using water as our reference. So we've got water freezing, and then at 100 degrees Celsius we've got water boiling. Okay, and there's some especially with water boiling here, we're talking about at sea level, 1 atmosphere of pressure and all that kind of thing, because the boiling point of water does change with altitude. So, and the other thing I did mention was at 4 degrees Celsius, water is dense, the most dense it is. And again, that's another good reference point, because what is density? Density is the grams per mil. Okay, so what does that look like? We've got 1 cubic centimeter of water is equal to 1 mil, which is equal to 1 gram. Okay, and if we scale that up, because it's also worth doing this, 1 cubic meter is equal to 1,000 litres of water, which is equal to 1,000 kilograms, which is equal to 1 metric ton. Okay, so there we go. There's a bit of segue between mass and volume and now temperature. So they're important things to, I think they're important things to know and understand. So we can get into this in a little bit more detail here and think about our different measurements of temperature. And if you wanted to get really scientific, we might understand that temperature is the average kinetic energy of the molecules. But for here, we're just working with 3 different scales. And I think it's easy enough to sort this stuff out. So what we're thinking about is we're going to plonk 0 somewhere on this scale, maybe about there. And I'm going to write minus 273 degrees Celsius here, and I'm going to put water boiling here at 100 degrees, and then I'm thinking about what's happening in the sun here, because we all understand that it can get to thousands of degrees up there. But this is the interesting point here. How cold do things get? And this is about as cold as it gets. So it's interesting to have a scale where what doesn't proceed past a certain point. And that's where this idea of the Kelvin scale come into play. And we're going to, with the Kelvin scale, we're going to call minus 273 degrees Celsius, we're going to call that 0 degrees Kelvin, and we're going to call that absolute 0. Okay? So everything is measured from that point, and here is your conversion here. So what else do we need to know about this scale? What we need to know is that every 1 degree increase in the Kelvin scale is equal to a 1 degree increase in the Celsius scale. And so what has the Kelvin scale done? It's just probably to reset the starting point. with some scientific knowledge about how molecules work, and realizing that at minus 273 degrees there's no energy left in the system anymore. So that's what that's about. The other common scale, and I might just have to clean the board here for a moment. So we've done the Kelvin scale, and what we want to do now, because often when you watch TV and you're watching an overseas channel, they have measurements in Fahrenheit. So that's an older scale, and I'm just going to write that out here. And we need to be able to convert between the two. So here's the things that I remember. At 32 degrees Fahrenheit, that's when it's equal to 0 degrees Celsius, and that's when water freezes. Okay, so that's a landmark that we need to remember, and if we remember that, we're off to a really good start. And by the same token, we've got this other measurement here at 212 degrees Fahrenheit. That's when water boils. So we need to be able to convert between the two, and I think they give you in degrees Celsius. They have a formula like this. They set it up like this: minus 32, where you put in the degrees Fahrenheit, subtract 32 from it, and then multiply it by a fraction of 5 over 9. Now, what I like to do is set this up slightly differently, because I, for some reason, like having my fraction out the front, and mathematically it's all still the same thing. That's how I like to set it up. And why I like doing that is because when I create, I'm going to do it in a different color, and I'm going to do it underneath actually. When I convert between the two, I like to multiply by the reciprocal here. So that is going to be the same thing as 9 over 5 degrees times the degrees Celsius. And on this side I've left with this. And the opposite of subtracting 32 is adding 32. So what I've got, and it all looks like a bit of a mess here, but I'm going to add 32 on the other side of that, and that'll give me my degrees Fahrenheit. So I'll change color, because it might be, you might be having trouble working through that or understanding that. So I'll write it again, and put it in this way, over 5 plus 32. And you might work with that a little bit easier. So given one thing, it's really interesting that I'd like you to practice this actually, is rearranging a formula so you can convert between the two. So we can check that it is working okay, because we know something. Okay, we're up here and we know a little bit. And so if I put 0 degrees in here, I should expect to get this equal to 32. So let's double check. So 9 times 0 is 0, divided by 5 is all 0, plus 32. Well, that's my answer. So it's a great way of checking that you've rearranged the formula correctly by just knowing a couple of little things. And that's one of the things that I hang on to, and I remember when I'm converting between degrees Celsius and Fahrenheit, is that when water freezes and when water boils in those two different scales. So good luck with those questions.